Chapter 5 Portfolio Mathematics. In the previous chapter, we looked at how to calculate the expected value and the expected variance of a single asset. Now we look at how to calculate the expected return and the expected variance of multiple assets when we have multiple assets in our portfolio. Then we look at forecasting the covariance from joint probability function. Then at last, we look at various portfolio risk measures and the applications of the normal distribution. Second section, which is portfolio expected return and variance. In this section, we will calculate and interpret the following things. Earlier we looked how to calculate the expected return of individual assets. Now we look how to calculate the expected return of portfolio. Then we look how to calculate the expected variance and the expected correlations of portfolio returns. So starting with the expected return of a portfolio, let us directly look at an example. In a portfolio, we have three assets: the S&P 500, long-term corporate bonds, and MSCI EAFE. And their weights in portfolio are 50%, 25%, and 25%. So if our portfolio is worth $1 million, then it means that $500,000 is invested in S&P 500, $250,000 is invested in corporate bonds, and $250,000 is invested in MSCI. So these are the weights of each asset, and this is the expected return of each asset. So the expected return of this portfolio equals to the return or the expected return of S&P 500 multiplied by its weight plus the expected return of the corporate bond 6 multiplied by its weight plus expected return of MSCI multiplied by its weight. So we get the expected return to be 11.75%. So expected return of a portfolio with n assets is, this is how the expected return is represented by. It equals to weight of asset 1 multiplied by the expected return of asset 1 plus weight of asset 2 multiplied by the expected return of asset 2, and so on. Now we will look how to calculate the expected variance of portfolio returns. So the expected variance of a portfolio with n assets is given as follows, where I and j represent assets. So suppose we have two assets in our portfolio, asset A and asset B. So we will substitute each asset with I and j. So let us see how do we write the formula. We take weight of asset A. We also substitute j for asset A multiplied by covariance of return of asset A with return of asset A. Then we take weight of asset A and now we substitute j for asset B. Weight of asset B multiplied by covariance of return of asset A with return of asset B. Then we substitute I with B. So weight of asset B against weight of asset A multiplied by covariance of RB with RA. Then we substitute J with B. So weight of asset B multiplied by weight of asset B multiplied by covariance of asset B is written with asset B. So when we have two assets in a portfolio, this is how we write the formula. This can also be written as weight A squared multiplied by covariance of return A with return A. So if you remember the formula of covariance, covariance equals to the summation of asset A's return 1 minus asset A's expected return or the sample mean return multiplied by asset B's return 1 minus the sample return of asset B divided by n minus 1. But because we are calculating the covariance of asset A's return with asset A, we can replace B with asset A. So the formula will be asset A's return minus the sample mean of asset A divided by n minus 1. So we can write it as summation of asset A's return minus the sample mean of asset A squared divided by n minus 1. So this is the same as variance of asset A. So covariance of asset A's return with itself is nothing but the variance of asset A. So I will write variance of asset A. These two terms are the same. Covariance of asset A with asset B is the same as covariance of asset B with asset A. So I can write it as 2 multiplied by weight A, weight B, covariance of asset A's return with asset B. I can write this term over here as weight of asset B squared multiplied by the variance of asset B. So when you have two assets in a portfolio, this formula can be expanded into this, and then this can be written as this shortcut over here. Now what if we have three assets in a portfolio? Although there is a very rare chance that you will be asked to calculate the variance of a 3-asset portfolio, but still let us see how do we calculate the expected variance of a portfolio with 3 assets. So say we have 3 assets A, B and C. So substituting I and J with each of the assets, we get weight of A multiplied by weight of A multiplied by covariance of A with A. Then weight of A multiplied by weight of B multiplied by covariance of asset A's return with asset B's return. Then weight of A multiplied by weight of C multiplied by covariance of asset A's return with asset C. Now we substitute I with B. Weight of B multiplied by weight of A multiplied by covariance of asset B's return with asset A's return. So we get the total formula as this. In total we have 9 different terms and we add each of them. And then we get variance of a portfolio with 3 assets. This formula can further be summarized as this, where you take weight A squared multiplied by variance of asset A. So this is the term we summarized. Then we take the second term, which is this, weight B squared multiplied by variance of asset B. Then we take the third term, weight C squared multiplied by variance of asset C. Then taking this term and this term over here, we get 2 multiplied by weight of A multiplied by weight of B multiplied by covariance of asset A's return with asset B. So this is how the formula when summarized looks like. So there are few observations that we can derive from this, that if a portfolio has n asset, then it will have n variance terms. So for example, when we had 2 assets in our portfolio, we had 2 variance terms. And now when we have 3 assets, we have 3 variance terms. And in a portfolio with n assets, we have these many covariance terms. So in a 3-asset portfolio, we have 3 multiplied by 3 minus 3, which is 6 covariance terms. So if you see, we have 1, 2, 3, 4, 5, 6. We have 6 covariance terms and these are the variance terms. And we have n multiplied by n minus 1 divided by 2 unique or distinct covariance terms. So this covariance term, that is covariance of asset A's return with asset B's return, is repeated twice. And similarly, this term is also repeated twice, which is this, and even this term is repeated twice. So we can see that In total, we have 3 unique covariance terms. So in a 3 asset portfolio, number of unique covariance terms are 3 multiplied by 2 divided by 2, which is 3. So in a portfolio with 20 assets, we will have 20 variance terms, we will have 380 covariance terms and 190 unique covariance term. So portfolio with n assets will have n variances, these many covariance terms and these many unique covariance terms. So from the formula we can say portfolio's variance is influenced by variance of individual assets expected return as well as the covariance between the assets expected return, and the influence of the covariance increases as the number of assets increases. So in a 3 asset portfolio we had 3 variance terms and 6 covariance terms. In a 20 asset portfolio we have 20 variance terms and 380 covariance terms. So as number of assets increases, the influence of covariance on the portfolio's variance increases. And a positive covariance term increases the risk, that is, increases the variance of a portfolio, whereas the negative covariance term decreases the risk, that is, decreases the variance of the portfolio. And this is referred to as the diversification benefit, that is, decrease in variance of the portfolio due to covariance is referred to as diversification benefit. Continuing with the previous example, let us see how do we calculate the expected variance of the 3 asset portfolio. This is the covariance matrix. So this term 400 represents the covariance between S&P 500's return and S&P 500's return. So this is nothing but the variance of S&P 500. This term over here is again the variance of the corporate bond, and this is the variance of MSCI EAFE. And this term is the covariance between S&P 500 and corporate bonds, and this is the covariance between S&P 500 and MSCI. So this is how the covariance matrix looks like. Now let us calculate the expected variance of the portfolio. So the variance of portfolio equals to, so this is the formula, and substituting the values we get, so we take weight of S&P 500 multiplied by variance of S&P 500, weight of the corporate bond multiplied by variance of corporate bond, weight of MSCI multiplied by variance of MSCI. Then we take 2 multiplied by weight of S&P 500 and weight of the corporate bond multiplied by the covariance between the corporate bond and the S&P 500. Then again we take the weight of S&P 500 and weight of MSCI. Then we take the covariance between MSCI and S&P 500. So we get the variance to be 195.875, and the standard deviation equals to root of this value. So the standard deviation is 14%. This value over here was in percentage squared, and we get the standard deviation in percentage terms. So this is how you calculate the variance or the expected variance of the portfolio when we have 3 assets. So let us calculate the expected correlation of the portfolio returns. So this is how the correlation is represented by, and the formula is covariance of 2 variables divided by the standard deviation of the first variable multiplied by standard deviation of second variable. This is called as the expected correlation because we are calculating this correlation using the expected covariance and the expected standard deviation of the 2 variables. So this was the covariance matrix that we had seen earlier. So let us find out the correlation between each of the 3 assets. So the correlation between S&P 500 and S&P 500 will be, the covariance, which is 400, divided by the standard deviation of S&P 500 and standard deviation of S&P 500. So this term here is nothing but the variance. So if we take the root of this, we should get the standard deviation of S&P 500. So standard deviation of S&P 500 is 20 multiplied by 20, and we get the correlation to be positive 1. Now let us calculate the correlation between S&P and corporate bonds. So the correlation equals to 45 divided by the standard deviation of S&P is 20, and this is the variance of the corporate bond. So if we take the square root of this, we should get the standard deviation of corporate bond. So the standard deviation comes out to be 9, and we get the correlation as 0.25. So similarly, we can calculate the correlation of all the other remaining terms. I want you to solve this example. You can pause the video and solve the example. So if you have solved the question, the answer to question 1 is 27. And the formula that you use is covariance equals to the correlation between two variables multiplied by the standard deviation of variable 1 multiplied by standard deviation of variable 2. So the answer is 27. Answer to question number 2 is, if Sintara puts 100% of her investment in stock 1, then the portfolio's expected return and the standard deviation will be the same as stock 1's expected return and standard deviation. And if she puts 100% of her investment in stock 2, then the portfolio's expected return and standard deviation will be the same as stock 2. Now answer to question 3 is, the variance comes out to be 99.72% squared, and the standard deviation is square root of this value. So US and Spanish bond returns measured in the same currency units have standard deviation of 0.64 and 0.56 respectively. If the correlation between them is 0.24, then what is the covariance of return? So covariance equals to the correlation multiplied by standard deviation of each of the asset returns. So 0.64 multiplied by 0.56, and the correct answer is option A, which is 0.086. The covariance of return is positive when the returns on two assets tend to have the same expected value, they tend to be above their expected value at different times, or they are on the same side of their expected value at the same time. So if you remember the formula of covariance equals to the summation of, say, variable x return minus the sample mean of variable x multiplied by the second variable, say y, minus the sample mean return of variable y. So suppose variable x return is greater than its sample mean return, then we have a positive figure, and at the same time variable y's return is greater than its sample mean return, then we have positive figure. So we get the covariance to be a positive number. And if variable x return is lower than its sample mean return, we have a negative figure over here, and at the same time if variable y's return is less than its sample mean return, we will have a negative figure. So the correlation comes out to be a positive number. So if both the variables are above their sample means at the same time, then we will have a positive variance, and if both the variables are below their sample mean at the same time, then also we will have a positive covariance. So the covariance of return is positive when the return on two assets tend to be on the same side, that is either above their expected value or below their expected value. When this happens, the covariance of return is positive. Which of the following correlation coefficient indicates the weakest linear relationship between the two variables? So correlation ranges from -1 to +1, and a correlation of 0 indicates that there is no linear relationship between the two variables. So if the correlation is somewhere closer to 0, it indicates a weak linear relationship, and if the correlation is closer to either -1 or +1, it indicates a strong linear relationship. So option B, which is -0.24, is the correct answer. So this is the weakest linear relationship among all the three options available. So you can solve this question, and if you have solved the question, the correct answer is option C. Question 5. All else being equal, as the correlation between two assets approaches +1, the diversification benefit decreases, stays the same, or increases. So if you remember that if the covariance is positive, then the portfolio's variance increases, and if a portfolio's variance is high, it means that risk is also high. And similarly, if covariance is negative, then the portfolio's variance decreases, so risk is also low. So when we have a correlation which is +1, then the diversification benefit decreases. So option A is the correct answer. The correct answer to question 6 is option A. The correct answer to question 7 is option C. And the answer to question 8 is option B. And for question 9, it is option C. Section 3, forecasting covariance from joint probability function. So before entering into section 3, there are some basic points about joint probability that I want you to understand. Suppose I have two events, event X and event Y. These two events are independent of each other. That is, event X does not depend on the occurrence of event Y, and event Y does not depend on the occurrence of event X. They both are independent of each other. Suppose the probability of event X occurring is 70% and probability of event Y occurring is say 80%. Then what is the probability of both of them occurring together? That is, what is the probability of X and Y occurring together? We call it as the joint probability. So when two events are independent, the joint probability equals to the product of their individual probabilities. So 0.7 multiplied by 0.8, which equals to 56%. So probability of both the events occurring together is 56%. If X and Y are independent or uncorrelated, then the joint probability of these two events equals to the product of their individual probabilities. So suppose I have two assets, asset X and asset Y. X can have two possible returns in the upcoming year. X can either generate 10% or it can generate 8%, and Y can generate either 15% in the next year or it can generate 13% in the next year. And the probability of X generating 10% return is 35%, and probability of X generating 8% is 65%, and probability of Y generating 15% return is 40%, and probability of Y generating 13% in the next year is 60%. So let us calculate the expected return of asset X and asset Y for the next year. So the expected return of asset X equals to product of these two plus the product of these two. So we get the expected return to be 8.7%, and similarly solving for the expected return of asset Y, we get 13.8%. Now let us draw a joint probability matrix. So this is how a joint probability matrix looks like. We have X over here, Y over here. X can either take two values, it can either generate 10% or 8%. Y can either generate 15% or 13%. So the probability of X generating 10% and probability of Y generating 15% together is the product of 35% and 15%, which gives us 14%, and the probability of X generating 10% return and probability of Y generating 13% return together is 35% multiplied by 60%, which equals to 21%. And similarly, we can fill the remaining matrix. So there is 26% probability that X generating 8% and Y generating 15% together, and there is 39% probability that X generating 8% and Y generating 13% together. So this is how the joint probability matrix looks like. Now let us see, based on this joint probability matrix, how do we calculate the expected return of each asset. So expected return of asset X equals to 10% multiplied by this joint probability plus 10% multiplied by this joint probability plus 8% multiplied by this probability over here and 8% multiplied by this joint probability over here. So if you add all of them, we get the expected return to be 8.7%. Similarly, calculating the expected return of asset Y, it equals to 15% multiplied by the joint probability of 14% plus 15 multiplied by 26% plus 13 multiplied by 21% and 13 multiplied by 39%. So we get the expected return to be 13.8%. So you can see the answers are the same when we calculated the expected return using this information and when we calculated the expected return using the joint probability matrix, the answers are the same. So this was the case when X and Y were independent. Now what if X and Y are dependent? So suppose Y is dependent on X. Then joint probability of them occurring together is probability of X multiplied by probability of Y given X. So suppose we have the following data. Suppose I have two assets, asset X and asset Y. Asset Y is dependent on asset X, that is, return of asset Y are influenced by returns of asset X. Asset X can have two following outcomes in the next year. Asset X can generate either 5% return or 20% return, and asset Y can generate either 10% return or 15% return. Because asset X is independent, so the probability of asset X generating 5% is say 40% and it generating 20% return is 60%. Now because asset Y is dependent on asset X return, so the probability of asset Y generating 10% return given that asset X has generated 5% return equals to 80%, and probability of asset Y generating 15% return given that asset X has generated 5% return equals to 20%. And similarly, probability of Y generating 10% given that X has generated 20% equals to say 70%, and probability of Y generating 15% return given that X has generated 20% equals to 30%. So let's form the joint probability matrix. We have X over here and Y over here. X can have two possible outcomes. Either it can generate 5% or 20%, and Y can generate either 10% or 15%. So the joint probability of 5 and 10 equals to 40% multiplied by 80%. We get 32%. And joint probability of 5 and 15 equals to 40% multiplied by 20%, which is 0.08. Similarly, 20 and 10, we multiply 60% by 70%, we get 42%, and here we get 18%. So from this joint probability matrix, how do we calculate the expected return of x and y? So just like we calculated previously, we will use the same method. We multiply 0.32 by 5%, 0.08 by 5%, 0.42 by 20%, and 0.18 by 20%. We add them all and we get expected return of asset x. And similarly, we can calculate the expected return of asset y. So on your exam, you won't be asked to form this joint probability matrix over here. You will be only required to calculate the expected return based on the joint probability. But just so you know how this joint probability matrix is formed, I have taken this example. Until now, we have used the term independent and uncorrelated alternatively. But technically speaking, they both are different. When I say asset X and asset Y are uncorrelated, this means that both of them don't have any linear relationship, but it is possible that there are some other relationship. They can have curvilinear relationship or any other form of relationship. So it is possible that they might be uncorrelated but not independent. But if I say asset X and asset Y are independent of each other, this means they don't have any sort of relationship among them. Neither there is any linear relationship nor any sort of curvilinear relationship. So technically speaking, independent and uncorrelated are different. But still throughout the curriculum, they both are used interchangeably. So now we come to the main part of section 3, which is to forecast the covariance from the joint probability function. Until now, we were directly given the estimated covariance. So if you remember the calculation of the expected variance and the expected correlation, we were directly given the data of the estimated covariance. Now let us see how do we estimate the covariance from a joint probability function. So we have the joint probability function or the joint probability matrix of two variables, the bank ops return and the new bank's return. So these two variables are dependent and this is their joint probability function. So RA is the return of bank cop and RB refers to the return of new bank. So bank cop can have three possible return outcomes and new bank can also have three possible return outcomes. So the joint probability of this 25% and 20% is 0.20. The joint probability of 25% and 16% is 0 and so on. So the first step in forecasting the covariance from this joint probability matrix is to calculate the expected return. So the expected return of bank corp equals to, we take 25% multiplied by 0.20, we take 25% multiplied by 0, and we have 9 such products. We add all the 9 products and we get the expected return of bank corp. But out of the 9 products, we can see 6 products will be 0. So it doesn't make any sense to add them. So the expected return of bank corp will be 25% multiplied by 0.20 plus 12% multiplied by 0.50 plus 10% multiplied by 0.30. So the expected return will be 14%. And similarly, expected return of new bank will be 15%. So this is the first step in forecasting the covariance. So after you have forecasted the expected return, you calculate the deviation of each possible outcome from the expected return. So the first possible outcome is 25% and the first possible deviation is 11. So similarly, we have two more deviations, and we also calculate the deviation of each outcome of the new bank's return from the expected return. So we have three deviations. Then we multiply each of the deviations and we get this. If you remember the formula of covariance, covariance equals to the sum of the product of all the deviations, that is xi minus the x bar multiplied by yi minus the y bar divided by n. So when we divide the sum by the number of observations, we implicitly assume that there is equal probability of each deviation occurring. So in this case, if we divide the sum of all the deviations by 3, then we are implicitly assuming that there is 33.3% chance of the deviation being 55 and 33.3% chance of the deviation being -2 and so on. But that's not the case over here. The joint probability, that is, there is 20% chance that the bank op's return could be 25% and the new bank's return could be 20%. So this means that there is 20% chance that the deviation could be 55. Similarly, there is 50% chance of the bank op's return to be 12% and new bank return to be 16%, the joint probability. So there is 50% chance that the deviation could be -2. So we take the product of the deviation and the joint probability and we get the probability weighted product. So these are the three probability weighted products. We add them all and we get our covariance. So the first step in calculating the covariance is that we solve for the expected return of each asset. Then we calculate their deviations and then we multiply the product of deviation by the joint probability and then add all those probability weighted product to get the covariance. So on your exam, you will be given this joint probability matrix. Based on this, you need to calculate the covariance. So we are done forecasting the expected return of a portfolio, the expected variance, the correlation of a portfolio return. Now we look at some of the portfolio risk measures. So before looking at the risk measures, let us understand the normal distribution in a little more detail. So this is how the normal distribution looks like. So this is the normal distribution where this is the y-axis and x-axis. X-axis represents the returns and y-axis represents the frequency of the observations or percentage of the observations or the probability. So suppose I have an asset whose sample mean is 10% and a standard deviation of 2%. And this asset has a normally distributed data. So the middle point of this normal distribution is the mean, which is 10% in this case. So this becomes 8%, 6%, 4%, and say this is 12%, 14 and 16. So can I say that 10% is 0% away from the mean, or I can also say that it is 0 standard deviation away from the mean. So I can write it as 0. Similarly, 8% is 2% away from the mean, or 8% is 1 standard deviation away from the mean. So I can write it as -1. Similarly, 6% is 2 standard deviations away from the mean, -2 and -3. Similarly, I can write it as +1 standard deviation, 2, 3 and so on. So in a normal distribution, we know that the distribution is symmetrical around its mean. That is, 50% of the observations lie below the mean, 50% lie above the mean. Or I can say 50% of the observations lie below 0 standard deviation and 50% of the observations lie above the 0 standard deviation. So just like in a normal distribution, it is always fixed that 50% will lie below the 0 standard deviation and 50% will lie above the 0 standard deviation. It is also known that the percentage of observations between 0 and 1 standard deviation will be 34.87%. Similarly, the percentage of observations between the 1 deviation and the 2 standard deviation will be 13.67%, and the percentage of observations below 2 standard deviation will be 2.28%. So because the distribution is symmetrical around its mean, the percentage of observations between 0 and positive 1 deviation will also be 34.87%, and this will be 13.67%, and this is 2.28%. So you don't need to remember the percentage of observations which lie between standard deviations or below a standard deviation. We have a table which shows us the percentage of observations lying below standard deviation. So this is the table which shows us the percentage of observations which lie below a stated standard deviations. So this table is about the positive standard deviations. That is, this table tells us the percentage of observations lying below these standard deviations which are to the right side of the 0. So on the left side we have standard deviation and on the right side we have standard deviation. So let us see how do we interpret this. So 0 standard deviation, we know that 50% of the observations lie below the mean or below the 0 standard deviation. So here also it is given that 50% of the observation lie below 0 standard deviation. Now 0 plus 0.03, which means 51.20% of the observations lie below 0.03 standard deviation. Similarly, taking 0.40 plus 0.06. So 67.72% of the observations lie below 0.46 standard deviation. Similarly, 1.3 plus 0.05. So 91.15% of the observations lie below 1.35 standard deviation. And coming to the last deviation, say 3.60 plus 0.09. So almost 100% of the deviation lie below 3.69 standard deviation. So say 3.69 standard deviation lies somewhere over here. So you can clearly see almost 100% of the observations lie below 3.69 deviations. So this was the table for finding out percentage of observations below the positive standard deviations. This is a table to identify percentage of observations lying below negative standard deviation. So this table can be interpreted in the same way as we interpreted this table. And strictly this table is only for normal distribution. If we have skewed distribution, if we have any different kind of distribution, then we cannot tell with certainty what percentage of data lies below a particular standard deviation. Only in a normal distribution, it is known for sure that below a particular standard deviation, these many percentage of observations lie. But for different distribution, we have to find it on an individual basis. So we had some basic understanding of normal distribution. Now let us look at some of the portfolio risk measures. An investor is planning for retirement and she is concerned with the return falling below her minimum acceptable level of 2%. She has three alternatives available in front of her. Choose the one alternative which minimizes the risk of return falling below 2%. Assume that all the three portfolios are normally distributed. So we have three portfolios and it is assumed that they are normally distributed. And we are required to find out which of the portfolio minimizes the risk of return falling below 2% or which of the portfolio minimizes the probability of return falling below 2%. So let me draw a normal distribution for portfolio 1. This is the expected return of 5%. The standard deviation is 8%. So I can say negative 3% is one standard deviation away from the mean. So on this x-axis, which is returns, 2% lie somewhere over here. So let us find out how many standard deviation does 2% is away from the mean. It will definitely be less than one standard deviation. But let us find out how many standard deviation it is away from the mean. So we take the expected return and the minimum acceptable level, which is 2%. So we can say it is 3% away from the mean. So one standard deviation is 8% away from the mean. So 3% will be 3 divided by 8, which is 0.375. So we can say that 2% is 0.375 standard deviations away from the mean. Now, if you look at the table that we have seen earlier, the percentage of observations lying below 0.375 deviation is 35.57%. So one way to interpret is that 35.57% of the observations lie below this deviation, or there is 35.57% probability that the return could be less than 0.375 deviation, or I can say there is 35.57% chance return could be less than 2%, which is our minimum acceptable level. So similarly, let us find out the probability of return falling below 2% for the remaining portfolios. So for second portfolio, we need to first find out how many standard deviation, thus 2% lies away from the expected return of 8%. So we take 8 minus 2, which is 6, divided by the standard deviation of 8%, which gives us 0.75. Similarly, for third portfolio, it is 0.25 standard deviation. So the normal distribution of second portfolio looks like this, where we have 0 standard deviations. This is 0.75 standard deviations. So if you look the table, we find out that there is 22.26% probability of return falling below 0.75 standard deviation, or there is 22.26% chance of return being less than 2%. Similarly, for third portfolio, the normal distribution looks like this. This is 0 standard deviation. This is 0.25. So the probability of return falling below 0.25 standard deviation is 40.13%. Or I can say there is 40.13% chance of return falling below 2%. So for the first portfolio, the probability was 35.57%. So of the three portfolio, the portfolio which minimizes the probability of return falling below 2% is the best option. So portfolio 2 is the best alternative available. So the portfolio with the lowest probability is the correct option. And on your next slide, you will see that this figure that we calculated over here is referred to as the safety first ratio. Shortfall risk refers to the risk that the portfolio value or the portfolio return will fall below some minimum acceptable level, and this risk is measured by the safety first ratio. The formula of safety first ratio is the expected return of a portfolio minus the minimum acceptable return divided by the standard deviation of the portfolio. This is nothing but the number of standard deviation that the minimum acceptable return is away from the mean return of the portfolio. So higher the safety first ratio, lower the probability of return falling below the minimum level, and lower the SF ratio, higher is the probability of return falling below the minimum level. So let us look at the following question. A client has a portfolio of common stocks and fixed income instruments with current value of 1.35 million pounds. She intends to liquidate or withdraw 50,000 from the portfolio at the end of the year to purchase a partnership share in a business. Furthermore, the client would like to be able to withdraw the 50,000 pounds without reducing the initial capital of 1.35 million pounds. So this is what the client requires, that initially she invested 1.35 million pounds, and at the end of 1 year the portfolio value should be such that if she withdraws 50,000 pounds from it, the value should still remain 1.35 million pounds. So the value should be 1.4 million pounds at the end of 1 year. So there are 4 possible allocations available, and it is assumed that all the 4 allocations are normally distributed. So address the following question assuming that all the 4 allocations are normally distributed. So given the client's desire not to invade the 1.35 million pounds, what is the shortfall level? That is, what is the minimum acceptable level? So 50,000 divided by 1.35 million. So the minimum return that the client requires is 3.70%. So answer to question 1 is 3.70%. According to the safety first criteria, which of the allocation is the best? So for all the 4 allocations, we are required to calculate the safety first ratio, and the allocation with the highest safety first ratio is the correct allocation. So for allocation A, the safety first ratio will be 16 minus 3.7 divided by 24, which equals to 0.5125. For B, it is 0.48. For C, it is 0.525. For allocation D, it is 0.48. So allocation C has the highest safety first ratio. So allocation C is the most appropriate. Question C. What is the probability that the return on the safety first optimal portfolio will be less than the shortfall level? So we are required to calculate what is the probability of return falling below 0.525 standard deviation. So using the table, we are required to use this table over here. We are required to find out the probability of return falling below 0.52%. 0.52 standard deviation. So we can see that there is 30.15% probability that the return could be below 0.52 standard deviation. So the probability that the return on the safety first optimal portfolio less than the shortfall level is 30.15%. So question 2 is similar to question 1 that we have just seen. So I want you to solve this question by yourself, and if you have already solved it, option B is the correct answer.